All right, everybody. Next, we have group 2, and they're going to tell us about F-pure and the diagonal thresholds for binomial edges.
Okay, good morning, everyone. First of all, I want to thank the organizer for giving us this opportunity to present. And at the title, we are going to talk about F-pure and diagonal threshold. And our team is confirmed by Jonhy, Richie, Daniel, and me. And we also have contribution from Adam LaClair, that is sitting there. So these two thresholds are some important invariants and P characteristics. So they measure the singularities of the rings. And in this case, they are also going to give us combinatorial data from the graphs, as we are going to consider binomial trivials. First of all, I want to introduce some notation. First is we are going to consider G to be a simple graph with vertex set up to N and the edge-side AJ. And also we are going to consider perfect fields with characteristic P and the binomial HIDL JG that is going to be contained in this ring S generated by the variables. And we are going to say M is the irrelevant ideal of the ring S, and M is the irrelevant ideal of the quotient ring AJ, that is F, or the binomial HIDL. Other rings are going to be commutative with identity, criterion, and prime characteristics. Now we define the F-pure threshold. But for this, this is only defined for F-pure rings. So first, we must know what F-pure is. And for this, we consider reduced rings and consider the P root set for an element of the ring. And we say that the ring is F-pure if the natural inclusion of R module speaks. That means that we can write to the 1 over P as this decomposition of R in R module. And we also need another definition, that is this idea of IE, that basically is to take all linear mass for R over 1 over P to the E to R and check if you apply to this element, it remains in the maximal idea. And now we can define the F-pure threshold. And this was defined first by Nave, where we are going to use the definition from the Stephanie and Núñez Vendelcourt. And for this, we consider F-pure ring, and we first define this invariant here, the BM invariant, that is the power T, such that n to the T is not containing this set IE. And the F-pure threshold is, well, this increases as order P to the E. So when you divide by B to the E, this sequence is actually bounded and is non-decreasing. So the limit at 6, and that limit is what we call the F-pure threshold. So this measures the speaking order of the maximal ideal. And our question is for graph that we know that the quotient ring is F-pure. Do we know something about the exact value? And there is some previous work that is for closed graph. And basically, a closed graph, you can think of this as if you have two edges and they share a common endpoint, then they must have another edge joining the other two endpoints. So this is an example of a closed graph, and we cannot get a closed label for the network. And the result is by René González Martinez. And the result says that if we have a connect closed graph, then the ring is going to be F-pure, and the F-pure threshold is actually equal to 2. And we want to extend the result. And we did it for the following family of graphs. And these graphs are the almost closed graph. And this satisfies these two conditions. First is if you have two vertex labels that are connected par, then you must have that all the vertex in the middle must be connected to the highest label one. And the second condition is that if you have your I vertex connected to the M vertex, that is the highest label one, then the I must be connected to all the vertices in between. So this is a bigger family than the closed graph, and we have several examples of families that are almost closed, and are the closed graph, complete multipartite of this form, generalized pendant cliff graph, and also caterpillar graph, threshold graph, and graphs with two associated terms. Then one of our main results is that if the graph is closed, is connected and almost closed, then the ring is going to be F here, and the S threshold is exactly equal to 2. And for this, the key step is proving that this monomial here, in terms of the generators of the binomial HID out of this p-1 power, is contained in this column ideal here, but not in this ideal here. And we apply another formula that gives us a value for the PM invariant, and then the result follows.
So another case in which we are interested is when the threshold of the ring AG is 0. And for that, we have to study the minimal primes of the binomial ideal, and those are related to something called cutsets. So we are going to talk more about that later, but for now, let me define what a cutset is. So for any set of vertices S, we set COS to be the number of connected components of G minus S. And we say that S is a cutset if that inequality holds. So basically here says that if you remove S and add back any vertex of S, the number of connected components strictly decrease. So we were interested in knowing when a vertex is in a cutset, but that's in general hard to determine. But we arrived to a complete characterization of that, and for that we need the next definition. We say that a vertex V is P3 if there exist two distinct vertices U and W, such that UV is an edge, VW is also an edge, but U and W is not an edge. So that's the picture to have in mind. And it's called P3 because if you take the inverse graph on those three, it's a P3 graph. And we have the following result. For a vertex B, the following are equivalent. B is a P3 vertex, B is in a cutset, and B is in at least two maximal cliques of G. So the condition of being P3 is easier to check than being in a cutset. You just need to check among all the neighbors and see if there are two that are not connected. And with that in mind, we prove the following. If every vertex of G is P3, then the threshold of AG is equal to 0. So the key proof of this is use the pre-realization to show that every vertex of G is in a cutset, and from that we can deduce that the ring of pictures of AG has only one splitting of degree 0, and we get this one applying a formula in the literature. So we can bound the threshold of AG by the threshold of the polynomial ring over the irrelevant ideal, but you are killing all the variables, so that's just the field, and that one has threshold equal to 0. And a family of graphs that satisfies this are complete multipartite graphs that are not almost closed. So in total, we can show what is the pure threshold of all the complete multipartite graphs. Another approach that we took is trying to compute the pure threshold for some monomial ideals related to the binomial H ideal. So we're going to define these two. First, the initial ideal is generated by all the leading monomials of polynomials in the binomial H ideal. And here we are taking the graphical diagonal order. And we also have the generic initial ideal. For this, is only relevant that is generated by this sort of monomials. Xi, xj, and a bunch of y variables, where this is a path in the graph. And for these two, we have the exact value of the pure threshold. So for any graph G, the threshold of G is the number of vertices that are not P3. And the threshold of the initial ideal, that one depends on the labeling, but it's the number of vertices that are either the first one or the last one and are not P3. So from here, we can see that those are always integers. The threshold of the initial ideal is always either 0, 1, or 2, and it's always bounded by the threshold of the generic initial ideal. And we have some further direction that we would like to continue for this problem. So for a graph G such that the ring AG is pure, we would like to find an example when we can show that the threshold is equal to 1. So we have some examples where we suspect that is one, but no one in which we can actually prove that is one. We also have the question if the F-pure threshold is always an integer. And also we are interested in knowing whether this inequality is true. So as I said, the inequality of gin over in, that's true. But for algegraphs for which we know how to compute the threshold of the binomial H ideal, this is true. So we will also continue to think about this.
So now we get to talk about the second threshold, which is the diagonal F threshold here. So before we allowed to define it, we have this preliminary definition. So for any ideal I of a ring R, the eth Frobenius power is this right here. It's generated by the p powers of the elements in the ideal. And since our ring is of characteristic p, we can verify that this actually is an ideal. So as an example, if you consider the relevant ideal here generated by these variables, it's a nice fact that the eth Frobenius power has the same generators but to the p power here. So this now allows us to define the diagonal F threshold. This was originally defined by Nebraska, Takagi, and Watanabe. So for each integer, e in like ring R, we define u of p to be the largest t, such that the tth power of m is not contained in eth Frobenius power. And this is analogous to the definition for the b's for the F pure threshold, with like the Frobenius power instead of the IE ideal. And so once again, we consider the limit of the new PE over PE, and the limit as z goes to infinity is what we call the diagonal F threshold. And we remark that this has been shown to always exist due to the work of De Stefani, Nunez, Betancourt, and Pérez. So our question is just calculating the diagonal F thresholds for the quotients of binomial edge ideals. So one reduction we can do is that a G reduces to like its connected components. Here, say like G1 to Gm. If you consider like the diagonal F thresholds for each of the individual connected components and add them up, we'll end up with a diagonal F threshold of the original graph. And so if we want to compute these diagonal F thresholds, we really only need to consider like connected graphs. And for like an explicit computation of the diagonal F threshold, we can explicitly do it for complete graphs and n vertices. So here we see that like for the complete graph and n vertices, if n is greater than 1, it's actually equal to just the number of edges, the number of vertices. There is like a degenerate case when like n equals 1, it's 1 more than number of vertices, and this will be like somewhat of, of course, an observation for us. And the key idea of this proof is that when you quotient out by the binomial F relations, you get these in the quotient ring like xi yj equals xj yi. And so we want like the m to the power of L, which is generated by monomials, to lie in like the Frobenius power. We can use these relations to like force some of the variables to have powers greater than or equal to the p to the e. And for complete graphs, we have like all the edges and hence like all the relations possible. So we can explicitly compute the new values, and these are the values we get. So the previous method is a bit hard to apply to an arbitrary graph, but thankfully we have like tools in general to like provide lower and upper bounds for the diagonal F threshold. So this first proposition gives us a way to give a lower bound for the diagonal F threshold. And for this, we actually only need to look at the graph itself. So we have like k independent. These are vertices with no edges between them. Then the diagonal F threshold is bounded below by 2 times k, or 2 times the number of vertices. And we also have a way of giving upper bounds. So if H is a subgraph of G that has the same vertex set, then the diagonal F threshold for H is an upper bound for the diagonal F threshold of G. And the nice thing about this is that we can often find subgraphs which have like components for which we already know how to like calculate the threshold. And we'll now see how we can like use these to calculate diagonal F thresholds for like previous graphs.
So by combining these two propositions, we can get an estimate for the diagonal threshold of JG. And it turns out that for many graphs, you can get an upper bound that's equal to a lower bound. And so for such graphs, we actually know the exact value of the diagonal F threshold. So for a concrete example of that, let's consider this graph on 6 vertices. So to get a lower bound for the diagonal F threshold, we want to look at independent subsets of the vertices. So for this graph, the largest independent set will consist of these 4 vertices, 1, 3, 4, and 6. And of course, there's no edges between any 2 vertices in this set, so this is an independent set size 4, and this gives us a lower bound of 2 times 4, which is 8. Next, to get an upper bound, we want to look at subgraphs for which we already know how to compute the diagonal threshold. So for instance, this is a subgraph of G, and notice that every connected component is complete with 2 copies of K1 and 2 copies of K2. And recall that the diagonal F threshold for K1 is 2, as is the diagonal F threshold for K2. And by the connected components proposition from a few slides ago, we know that the diagonal threshold for this subgraph is equal to 2 plus 2 plus 2 plus 2, which is 8. So this gives us an upper bound of 8 for the graph G. And so combined with the lower bound here, we get that the diagonal threshold is exactly 8. So this method actually works for lots of graphs G, but unfortunately it does fail for some graphs such as cycles with an odd number of vertices. But fortunately, we do have another method for computing diagonal thresholds, which works for any graph. And this method relies on the minimal prime decomposition of J. As we saw in Group 3's presentation, we can describe the minimal primes of a binomial edge ideal JG by using cut sets of G. So recall that for any subset A of the vertex set of G, we can associate to that set a prime ideal containing JG, which is given by this formula. So we have a prime PA containing G associated to the set A. And it turns out that PA is a minimum prime precisely when A is a cut set. And it also turns out that every minimum prime of G comes from this construction. So essentially describing the minimal primes of JG is more or less the same as finding all of the cut sets of G, which is a combinatorial problem. So how does this relate to the diagonal F threshold? So it turns out that for any binomial edge ideal JG, if we let the PAIs be the minimal primes of G corresponding to the cut sets AI, then the diagonal threshold of JG is equal to the maximum over the diagonal thresholds of all of the minimal primes PAI. And the reason this helps us is because we can easily compute the diagonal F thresholds of the minimal primes using this formula. So you just take the number of vertices, subtract the size of the cut set AI, and add the number of isolated vertices of the graph G minus AI. And actually, a corollary of this theorem is that the diagonal F threshold is always an integer for any graph G. So going back to this graph from before, verify that the minimal primes correspond to, there's 5 minimal primes which correspond to the cut sets, which are the empty set, vertex 2, vertex 5, the set consisting of 2 and 5, and the set consisting of 3 and 4. And the one that gives you the largest diagonal F threshold is going to be the set consisting of 2 and 5, which are highlighted here. So to compute the diagonal threshold for this prime, we just apply this formula from the previous slide. So, so we have 6 vertices. We have the size of the cut set is 2, and when we remove 2 and 5, we're just left with 4 isolated vertices. So the diagonal F threshold is going to be 6 minus 2 plus 4, we could say. And of course, this agrees with what we had before. Thank you.
Questions for the speakers?
You had mentioned that, like, for the F pure threshold, you focused on P3s. Was the focus on P3s only for when G is almost closed, or does this work for all graphs? G?
For all graphs. Okay. Yeah, that characterization of when a vertex is in a cut set works for any graph.
I also had another question. Sorry if this is a little bit vague, but when you were talking about F pure threshold for almost closed graphs, you took the element of the polynomial like f12, f23, all the way up to fn minus 1 fn, right? This is the same polynomial that group 3 was talking about, right?
No, almost the same.
Okay. All right. Sorry.
I mean, it's a certain kind of polynomial that is standard in this kind of things related to like determinantal ideals, and that's it's common to see it like in a lot of places.
Okay. For the diagonal threshold group, you said that in most cases you could get the upper bound given by a subgraph to be equal to the lower bound given by independent sets, right?
Yeah.
Are there any cases that you found so far where like you can't achieve equality using that method?
Like one example, I guess like in, just go back to this slide. Like I guess here by subgraphs, you mean like subgraphs, like
Maintaining all the ratios.
yeah, such that like every connected component is complete.
Yeah.
And I think this fails for cycles with an odd number of vertices. I think if you have C2n plus 1, then you can get a lower bound of like 2n and then like an upper bound of 2n plus 1.
Okay.
So like you almost know the exact value, but not quite.
Thanks.
Go ahead,
I remember last time you had some conjecture about like the well partition things plus like cycles with like adding something about the cycles, and because you did you say you knew how to compute the F3 threshold in a different way for the cycles, so you thought like I forgot. Can you remember?
Or yeah, we didn't talk about that conjecture in this presentation, but still something that we like to work on. We haven't been able to prove it yet.
Okay. Do you expect this still true?
Yeah, I think we suspect it's true.
Excellent. Another question? Okay, let's thank the speakers again.